Okay, hello everyone. So today we're going to start off talking about outlier analysis. So I'm going to draw our typical set of points over here, but this time maybe I'll add one extra point down here. So the idea is that our typical line might look something like this, but when I add this extra point here, it has a lot of influence on the fit. And so you may end up maybe with a line that looks something like this. And that would be the line that would sort of minimize, right, your squared error term. And because this point is so far out from the rest of the points, it has a much sort of larger influence. So when we think about identifying outliers, this might be visually obvious, this particular point, but what if a point were over here, right, or over here? How can we figure out a way to quantitatively determine or measure an outlier? So it turns out there's a couple different ways of doing this, and we're going to talk about two of the more common ways of identifying outliers. So the first is known as leverage. So this is how much a predicted value would change if the observation was shifted 1 unit in the y direction. And this measurement is always going to be between 0 and 1, just by virtue of how it's calculated. So we denote leverage by h. Looks something like this. So it is the fraction of the change in my predicted outcome versus or divided by the change in my yi. Okay, so the idea here, if I were to jump on back here, is that I would take this outlier point and I would shift it in 1 unit of y, and I would observe both how this changes and how my line might change. And so that may influence my line slightly to something like this. So that's the leverage term. And if you think about what this is doing here, if I have a bunch of points that look something like this, and a fitted line, really, this is going to care about points that are farther out from along the y-axis. So down here, up here. So these points are all going to have a large amount of leverage. Sorry, not y-axis, along the x-axis. And that's actually where the term sort of comes from, right? So if we think about a lever if I had some sort of balancing point here, this line will be more influenced the farther out I am along my x-axis. So that's one type of outlier. However, as you can imagine, the sort of closer I am to that pivot point, the points may actually have less leverage even if they are farther away. And so one way of capturing that is via something known as influence. So this is measured slightly differently. This is the effect of deleting the point. This is also known as Cook's distance. Okay, so Cook's distance, D, for every point. So again, this is a mathematical definition that you won't have to memorize, but we'll go through it anyways. Y hat J minus y hat J I, and I'll describe what that is in just a moment, times K MSE. So this term here refers to the fit without yi, and k is the number of coefficients. So in this particular example, if I were to erase the point, it's basically essentially a measurement of how my fit changes, and that corresponding difference, if it is really large, then your influence term gets bigger, right? So if I go back to the equation, if the difference between my yj hat and my yj hat with the point deleted is really large, that term here will get very large, and therefore it's saying it has a really large influence. If you delete a point and the line doesn't change very much, then in essence, the point has a small influence. And so both the leverage and the influence are quantitative methods that we can directly measure in order to determine whether or not something constitutes an outlier. And I'll talk a little bit later about what you would necessarily do with an outlier. Just because you identified it doesn't necessarily mean that you just get rid of it. There is often value to preserving the data, but again, this is typically pretty context dependent on your problem. Okay, so let's go to R. And let's figure out how to implement this. So I'm just going to quickly load a couple packages. Great. Okay, so we're going to run our typical regression data sets. So this is the same example we've been using the whole time, generating 100 random points between 0 and 50. We're going to have an error term randomly as randomly selected from a normal distribution with a mean of 0 and a standard deviation of 5, and our y is going to be x times 0.5 plus our deviation. And we do know what this looks like, right? Let's see, plot. Let me make that table really quickly. So x equals x, y equals y. And here, data equals 4 plots, and I will choose in my aesthetics what to assign on my x-axis and y-axis, and this is going to be a dot plot. So we go ahead and run this. We can see the points over here. Let me make the points a little bit bigger, so it might be easier to see. Great. So we know what this looks like. And this time I'm going to, let me also quickly do the regression. And we can see our typical estimates. Slope is about 0.5. Intercept is technically 0, but this isn't statistically significant. So all of this is totally fine. And one quick thing to note from last time, just as a thing to point out, I talked about the F statistic. When you only have one variable, your p-value is going to be exactly the same as what's shown for the standard error. In this case, I actually also have an intercept, so it's slightly different. But essentially, they're going to be testing a very similar hypotheses. Okay. Now let's see what happens if I add a single outlier. So here I'm going to concatenate an extra point onto my vector of x's. And I'm going to also artificially add a y. So I've added both of these, and I'll just go ahead and copy and paste my plot here. And let's see what happens. So now I've introduced hopefully what you can see as this very blatant outlier, right? And if I run the regression again, let's see what happens. So we can see the effect of adding just even a single point here. You have a much lower coefficient on my x variable, which makes sense, right? We would expect the slope that would fit all of these points to go down. And that's indeed what we see. And in fact, that also causes there to be a now non-zero statistically significant intercept. Okay. And as a result of that, we can see leverage. So this is the function that will essentially tell you what the leverage is. It is something called hat. You have to put it in matrix form, so that's what this is doing. But we're essentially extracting the information out of our model in order to measure that leverage value. And note that it's not simply identifying the outlier, right? It's actually going to figure out the leverage that corresponds to every single data point within within this model. And I can actually plot that, and we can see what that looks like here. And what you can see is that for every single point, there is some leverage value. And we can see that there is one up here that stands out quite a bit. And that that leverage value is indeed the one outlier that we artificially introduced into the data. The order of these is just the order in the data itself. And so you can see if I pull up the data table called for plot, the last point, the 101st point, is our outlier. And so that's 101 over here corresponding to this point. And so one of the ways that I can kind of determine whether something looks really out of place is visually with something like this. And in fact, you can use the leverage even in a multivariate situation because it corresponds to each index point. And so this contains information. Your leverage will contain outlier information across multiple dimensions. And that's handy because in those cases, unlike in this example, you may not be able to visually see in a plot the fact that a point is an outlier, whereas with the leverage, you would. And if I wanted to look at the corresponding X values with the leverage, you can do that, and it will tell you which one is your outlier. So these are the leverage values corresponding to each of the X values within my data. Cook's distance. So we'll do CD. You can use this function called Cook's distance, which is a measure of the influence. If I go ahead and run that, we can see that across each of the 101 values, you can find corresponding Cook's distances. Okay, and if I go ahead and plot that, that looks something like this. And once again, the same point in this case not only has a lot of leverage, it also has a lot of influence. And we can see that here. And it's the same idea with the index. The very last point, the 101st point, is the one that jumps out that corresponds to the point that we know to be the outlier. Okay, and so these are a couple handy functions that help you look at the data in a quantitative way to identify outliers. There's a question of where the cutoff needs to be in order to figure out when you would identify something as an outlier, but that's typically for that in itself can be somewhat of a subjective measurement when you would decide which value in order to think of something as an outlier. There are a couple like rough rules of thumbs to do these cutoffs. So for leverage, one that people use is 2k plus 2 divided by n, where k indicates the number of your predictors and n is the number of data points or your sample size. And for Cook's distance, there is a similar cutoff. So this would be for leverage. For Cook's distance, one cutoff that you can use is 4 divided by n for Cook's distance. These are not hard and fast rules. And again, just because you've identified an outlier doesn't necessarily mean that you should just get rid of it. It's important to understand what that outlier is doing in the context of your data set, and how it's specifically influencing your model. And so we want to think about outliers as a careful way of sort of diagnosing particular issues in the model, but not as a way to sort of blindly remove from your data set. All right. So that is our little bit about outliers. And the next piece that we'll talk about is multiple regression. Okay, so let me jump back over to my notes and to our whiteboard. So the next topic of the day is known as multiple regression. So we've kind of hinted at this here and there. This is an extension of our simple linear regression to predict the value of a variable based on the value of 2 or more other variables. So in other words, we have been talking about this idea where we have yi is equal to beta 0 plus beta 1 x1 I. And this is our intercept, with beta 1 being our slope. And all we're doing is adding more terms. So beta 2 x2i plus beta 3 x3i, so on and so forth, up into beta n. So this is our sort of generalized form of this, and plus epsilon I for our error term. So anything beyond having one x variable, we refer to as multiple regression. And the idea here is something like this. If I were to think about our original example, here we draw a fitted line through these points. And it is exactly analogous to a regression through multiple multiple dimensions. So if this is x1 and x2 and this is y, I can draw points uh, where the size of the point is kind of like how far away they are. So if I have something like this, okay. So essentially, hopefully you guys can kind of visualize this. Instead of a single line in 3 dimensions, I have kind of this plane. Instead of a line going through a bunch of points, it is now a plane extending through a bunch of points in 3-dimensional space. And the interpretation of a lot of what we've been doing doesn't really change, right? And that's kind of why we start with a single variable first. So when we think about y equals beta x plus alpha, or if I stick with our notation for today, beta 1, beta 0, this beta is an indication of as x changes by 1 unit, then y sees a corresponding change by beta, right? So for every 1 unit that x goes, we go up by beta, which is our slope. And when we think about what the coefficients mean on each of the successive betas, that interpretation actually remains the same. But you can kind of see pretty quickly, well, I could draw this particular example where I have 2 dimensions or 2 variables, but as I extend into larger dimensions where I have 3 variables, 4 variables, I've worked the models that have 1,000 variables. The ability to do the visualization kind of goes away, right? We can't really visualize that. However, it is really important to have those fundamentals from our univariate regression, right, with 1 variable, because all of those skills extend in a very straightforward way into multiple regression. Okay. So let me jump on back to R and let's look at example of multiple regression. So I'm going to switch on over right now. And we're going to look at example of multiple regression. And I think this hopefully will be a way of really being able to see the power of multiple regression and being able to identify some of these trends. Okay, so now I'm going to come up with a couple of different X data sets. So we'll do 100 like this. We're going to have 100 points that now are between 0 and 100. We'll repeat this randomly. And we will now generate 4 vectors instead of 1 vector of x's. And we'll have a different set of deviations or errors. Okay, so hopefully this is all fairly familiar territory at this point. We're going to generate a new set of data. Okay. And let me put this all together into a single table. So we'll have x1 equals x1, x2 equals x2, x3 equals x3, and x4 equals x4. And of course, y is equal to y dot multi. So now I should have a table with 5 columns, x1, x2, x3, x4, and y. So note that I've actually done something different here, or maybe less intuitive. Y is actually defined strictly as a function of x1 and x2, and not of x3 or x4. So let's see what this looks like plotted. So one moment here, let me pull something up. Okay, so we are going to generate 4 plots, and then we're going to put them all side by side. So everything is going to be coming from the same data set. And I'm going to plot essentially each of the x's against the y. And we'll do slightly bigger points. Okay, so I'm just going to copy and paste this a couple times. So we'll have 4 of these plots, and the x's will all be different. And we're going to plot them all together. Oops, I should call these plot 1, plot 2, plot 3, and plot 4. I haven't actually tested this in ggplot yet, so hopefully this all works out. Okay, great. So in this particular case, when I plot each of my x's against my y's, visually, I can actually see a really obvious trend right between my x2 and my y. But in fact, we know in ground truth, right, because we are the ones who defined it, that y is actually also a function of x1. But I think if you were to just look at the plots here, that would be really hard to determine, right? And so visually, if I were to provide this particular example and I say, okay, which variables influence or are related to my y outcome? Well, I think it'd be very obvious to say x2, but it would be much less obvious to say x1. And so this is where, our ability to sort of visually identify these trends kind of breaks down. However, the nice thing about the regression is it is very powerful in being able to essentially suss out these trends. And we should be able to see that when we run a regression against multiple data points. So let's do exactly that. So I'm going to regress y.multi against x1. And then in order to add multiple ones, you can do something like this. So this is a linear in parameters. And so I can just simply add up all the variables and it will create a coefficient for each one. And we can look at the summary. And what you will see is that unlike our ability to visually identify the trend between x1 and y, in this particular case, we can see the regression has no problem in being able to identify. And we can see, one, that they are both statistically significant. And we know, right, ground truth, the coefficient should be about 0.5 for x and about 2 for x2. Sorry, 0.5 for x1 and 2 for x2. And indeed, that is what we find here. And not only that, the regression also knows that x3 and x4 are not statistically significant. In other words, we are not confident at all that there is actually a relationship to be found between our x3 and y, as well as our x4 and y. And we can look at a bunch of the other metrics, right? R squared is pretty high, and we can see the p-value for our f statistic is extremely statistically significant, hence indicating that our model hypothesis that all of the betas should be equal to 0 is rejected. Okay, and so hopefully this is kind of a nice visual example of the fact that a multiple regression is a powerful tool that will identify trends that you can't really see visually. Okay. So we're going to look at a couple more things related to types of variables and interpretations. So let's hop back to the notes and the whiteboard. Okay, we're going to look at a couple of common types of variables and variable transformations. So when we talk about a linear regression, so something that looks like this, I've mainly been showing these really obvious examples of where you're going to have a line just kind of pass through a set of points that look like a line should essentially go, a straight line should essentially go through them. However, even though it is a linear regression, doesn't mean that the relationship strictly between x and y have to be linear. So if I were to, let me do it differently. So if I were to draw points that look something like this, you might think, well, if I just draw a straight line, maybe that's not quite as good as if I had something like that. And in fact, the way this is actually still a fairly common type of thing that you can have in a linear regression. And the way that we essentially do something like this, let's suppose that the true value of y is related to the square of x. So x squared is the true relationship. Well, I can, actually in this particular case, I guess it would be something like this. Oh, no, sorry, I had it right. So in this case, essentially what I can do is I can do a transformation of my points, but leave it in a form that's still linear in the parameters. So I can do something like this. So these values as inputs, these are just any sort of values corresponding to an input variable. Really what we care about is that the betas are linear. And these don't have to be, right? Because I could just redefine z equals x squared and then run a regression of y equals beta z. And to that end, this then allows me to encompass lots of different functional forms or functional relationships between x and y that don't necessarily represent a linear correspondence between the variables, as long as, again, these betas are linear, right? And so as long as these remain linear, then we're okay. You can't have something like x over beta. Or something like y is equal to square root of beta x. So these forms would not be allowed. So when you think about types of relationships between x and y, you can imagine that, yes, that there are sometimes linear relationships, but probably a more common type of relationship is one that is exponential in nature. So that is actually a very common type of relationship to see. And so the way that you could deal with that is to do a log transformation in order to linearize either my x's or my y's. And so let's look at these transformations and what that means for our interpretations. So interpreting logs in regression. So we'll start out with our default, which is called level. And so this is just our ordinary example that looks something like this. And so we've actually already talked about this earlier in the lecture. So delta y is equal to our delta is beta 1 times delta x. So in other words, as x increases by 1, y increases by beta. So the next example, oh, and I should mention that when I'm talking about logs in these regressions, I'm always kind of referring to natural log and not the log base 10. So log is, so anytime I'm saying log, we're talking about ln, not base 10 log. So ln of y is equal to beta naught plus beta 1 x plus epsilon. Okay, and the interpretation of this may look a little bit complicated, but actually there's a shortcut that is a very common thing to use here. So the way we interpret this, analogous to the way we think about a level, is a percent change in y is equal to 100 beta 1 times delta x. So in other words, as x increases by 1, y increases by 100 times beta 1%. So let's say that beta 1 has a value of, let's say beta 1 has a value of 0.1. In our level example, if x goes up by 1, y goes up by 0.1. In our log level example, as x goes up by 1, y goes up by 0.1 times 100, which equals 10. So y would increase by 10%. So where the heck does that come from? So this is actually an artifact of the fact that if I do a log of 1.01, this is very close to about 0.00995 or about 0.01. And so that change as I go up a single value is close to a percentage increase. But note that it's not an exact value. And so when we're talking about interpretations here of the log level, should always be careful because this is really in reference to a marginal change. So that's in this here is essentially a shortcut as an approximation for the marginal change in y as my x changes. It's helpful for interpretation, but do keep in mind that it's not an exact value. Okay, we can also have the level log. So this is y is equal to, stay with our notation here, beta 0 plus beta 1 times log of x plus epsilon. And in this case, it's a similar type of idea. Delta y is equal to beta 1 over 100% delta x. So the interpretation is as x increases by 1%, y increases by beta 1 over 100. And the last one is where you have a log, and so this might be log of y equals beta 0 plus beta 1 log of x plus epsilon. And if you're following the pattern here, then you can hopefully predict what is happening. Percent change in y is equal to beta 1% change in x. In other words, as x increases by 1%, y will increase by beta percent. So the log is a fairly common form, especially in econ. This is a way that you can measure an approximation of the elasticity value, right? So a percent change in one value leading to a percent change in another value, that is known as an elasticity. And when you have a lot of econometric type of regressions that are looking at these outcomes, oftentimes they are doing these log regressions that will essentially let you look at the elasticity as the main mode of relationship between variables. Okay, so that is our little aside about these common transformation forms. We will eventually kind of revisit this idea of transforming the data in order to keep ourselves in the linear regression space. This is a handy, flexible way of doing that, but still being able to retain one of the big benefits of our linear regression form, which is that interpretation. Everything that we're talking about here, changes in x's leading to changes in y's. It's a very straightforward way of interpreting a lot of these regression models. And we're going to see kind of how that eventually plays out into thinking about more sort of nonlinear regression forms. But that'll come a little bit later on in the quarter. Meanwhile, let's talk about one more thing for today. And that is our dummy and categorical variables. Okay, so we have primarily been talking about data that is arranged actually in a particular sort of way. And that is when I have something that looks like this. And inherently, we have been assuming that x is a continuous variable and that y is a continuous variable. There are other types of variables. You can have a binary variable, in which case our values can take 0 or 1. And we can have categorical. And actually, I should also mention this binary is also known as a dummy variable sometimes. So categorical variable is similar, except instead of 2 discrete values, it can take on n discrete values. So 1, 0, 1, 2, ... n. Okay. And so what we're going to do is we are going to, for today, think about the use of binary and categorical variables in X. Later on in the class, we will start to think about how this can also be for our response variable as well, for our Y. But that's going to come a little bit later. You have to use slightly different models that cannot be a linear model necessarily. And we'll think about why that is later on. So going back to this, for our x's, we have the ability to have a binary variable as just having 2 outcomes, essentially. You can have a 0 or 1. This might be like flipping a coin. You could have heads or tails, right? A categorical variable, slightly different. So this is a variable that can take a number of possible fixed values. So what are some examples of this, right? So like demographics. So if I wanted to talk about like education level, right? So this might be, did you get a high school diploma, a BA or a BS, right? So a bachelor's degree, a master's degree, a PhD, and so forth, right? So these aren't number values. We have these, we're talking about these as categories, and you can code them into like an integer set of values. But for all intents and purposes, right, this is not analogous to anything we've done before, where we've really been thinking about X as this sort of continuous set of variables. This could be like a political party, right? You could be Democrat, you could be Republican, you could be an independent, and so on and so forth. And in fact, I can even do combinations of continuous and categorical variables. And so that would be known as an interaction variable. And that might be something that we'll get to in the next lecture, but this is where you have 3 or more variables whose influence is not additive. Okay, So probably the best way of kind of getting a handle on uh, exactly what these variables are doing is simply to look at an example. And so we can do that in R. So give me a quick moment to switch on over. And we're going to look at essentially a real world example. Okay, let me make sure I've got my data. So we're going to look at something called wages. So this is a simple data set, and let's take a quick look at this. So this data set contains 6 variables. There are over 1,000 rows or data points, and each row contains information about a person's earnings, their height, their gender, race, education, and age. And indeed, we can take a look at some details about it. If I were to go through and sort of categorize each of these variables, we can kind of see what's going on here. So the earnings is a continuous variable. Our height is a continuous variable. However, the gender is only containing 2 outcomes. And so this would be a binary or dummy variable. Whereas our race, let's take a look. So unique wages for race. We actually have 4 unique races, and so this is a categorical variable. And then for education and age, these refer to the years of education that someone has received and the age, how old they are. These are technically integer variables, but we can basically just consider them as continuous. All right, so let's quickly make a wage model. So here, essentially what I'm going to do is I'm going to regress earnings on a person's education, their age, and their gender. And if I look at the summary of this, okay. Oh, I wanted to clear all the plots. There we go. Okay. So if we do our interpretation of the coefficients, we can see a couple things here. So it's a little bit less straightforward to draw directly. But the idea and the interpretation of this is that essentially for every year older a person is, they on average make $280 more. Right, so this is our beta, and the change in the outcome is you change x going up by 1, y increases by 280. And we can use a similar type of interpretation for education. So for every additional year of education someone receives, on average, their income increases by $4,469 on average. And we will note that these are all sort of statistically significant. Okay, there's kind of something interesting happening here for our intercept. And actually, let me actually simplify this a little bit. I'm actually going to take out the age factor and let me rerun this and then we can reinterpret this. So I've taken out the age and just focusing in on one continuous variable, so education. So similar results, it's basically saying every year, additional year of education you receive, the average annual earnings increases by $4,200. Okay, what does this intercept mean? And then there's this factor sex male thing going on here. So this interpretation is actually a little bit different, right? Because we're no longer dealing with a continuous variable. And so this particular example, essentially the way to interpret this is that for whatever person or category is indicated here, in this case male, then essentially you're saying if the person is male, then on average their earnings are $20,000, $20,430 higher than your baseline. And our baseline is female, because that's the one that's kind of missing here. Whatever is omitted from our factors is what is being taken as the baseline. And the default setting in R for the baseline is just in alphabetical order. And so because F comes first in female, that's getting omitted as the baseline, and everything else, in this case male, is being directly sort of shown in the output of the regression. And then we also have this large intercept, which basically means, you know, at our baseline with no education, you have a negative, you're basically starting at negative 31,880. Okay, that's kind of counterintuitive. So let's draw kind of what this means. So if I go over to the plots, oh, actually, I'm going to do this. So in this case, I will have an axis of education and earnings. And the fit is essentially going to look something like this, where the slope is equal to 4,239.9. And now I want you to think carefully about what this point is. And I'll give you a second. You can, I guess, pause the video if you want to think about exactly what this means. And in fact, really what you have here are two lines. So this actually also has a slope equal to 4239.9. Because over here in the results, that 20,430 is an indication of essentially a different intercept. And so if this was my female line, that's our baseline at our default intercept of negative 31,880. And over here, this line as an indication for the males. So this would be negative 31,880 plus 2430. And so what is that? So that would be 31,880 minus 20430. Oops. 20430. So this would be negative 11,450. So in this particular case, you have a male who, if they had 0 years of education, would start with a salary of negative $11,450. And if you were a female with no education, you would start at a salary of negative 31,880. And they would both earn $4,240 more per year of education that they receive. The negative income is kind of because, right, it's out of the bounds of the analysis, right? You don't actually have anyone with 0 years of education within the data set. But this is essentially the example of how we would go about interpreting the results. This part actually does get a little bit confusing, especially for folks who haven't seen dummy and categorical variables before. And so we're going to look at this in a little bit more depth next time, and also include some of the interactions as well. But one thing that I did want to do before we end for today. So I'm actually, let me go back to this model. And let's take a little bit about what we learned from before in terms of model diagnostics. I can look at things like, so this is the regression here when I put age back into it. And I can look at things like significance levels. I can look at the R-squared to do some general model diagnostics. But remember, one of the most powerful ones that I talked about was the residuals. And so that is important to look at as well. And we kind of see something a little bit weird going on. TRs do get sort of larger on one side, which isn't really kind of the end of the world. But what's probably more worrying is that there's like this weird sort of cutoff line happening. And so take a moment and again, think about why this particular thing might be happening. So one thing that I can do, especially to help corral some of the really high wage earners, is actually to do a log model. And that's a way of essentially normalizing data points that have like large differences in orders of magnitude, because the law will kind of put them all on the same scale. And if I run this model, I do have some NAs produced, and that's an artifact of when you log something that doesn't like to be logged, you may have points that essentially get dropped out. But let's look at the summary of this and reinterpret. And here we are changing our interpretations based off of that level, log level that I had talked about before. So for every year increase in your education level, your income goes up about 16%. For every year older you are, your income goes up a little bit less than 1%. And actually, if you are male in this data set, on average, you are making 99% or about double, right? 100% higher, or about double what female would be making. And if I were to take a look at the residuals, kind of curious to see what happens. Okay, so one of the things that I'll note is that the big spread that we're seeing at higher values of our prediction, or in other words, at higher earnings levels, is kind of eliminated, which is good. Generally, this kind of spread of points looks pretty decent, but you still do have a whole bunch of errors that look like kind of in this cutoff line. And what I will mention that is that these kind of artifacts actually do kind of show up when you have binary variables. You may see patterns like this, but this seems sort of explicitly striking. And one of the things that you can do is kind of look at the data and try to identify what points that these particular errors are corresponding to. And when you do that, one of the things that you'll notice is that these are all essentially corresponding to really low earners. There are a couple of points in this data, if you do a little bit of investigation, where you have actually a couple negative values. So this is where the log transformation failed before, because you can't take a log of a negative value. And you have some people earning like $1,000 a year. And so it's kind of clear that these people are not necessarily working sort of traditional jobs. This might be a part-time thing, right? And so in this case, in order to kind of make a more uniform data set where I know I'm examining, let's say, full-time workers, I can sort of drop these guys and see what happens to my model. So in fact, I'm going to go ahead and copy and paste all of this, except this time I am going to change the input data to only include people who make more than $1,500 in a year. So in this case, my numbers are changing a little bit. Now education accounts for like 12% instead of before what we were saying is 16%. And the age is still about 1%. increase in earnings for each year of age you are, but the big difference is that between men and women, that difference is now down to 45% instead of doubling. And the last thing that I'll do here is look at my residuals, and wow, look, this is so much better, right? I don't have that weird sort of line trend. These points seem to me to be fairly randomly distributed around 0. They're not sort of biased positive or negative much. And so, yeah, this is what I would consider a fairly innocuous looking residual plot. Okay. So the lecture actually goes by much faster without folks asking questions. But I do, hopefully, if you do have questions, we can get around to those at the beginning of lecture next time. I'm going to sort of purposely stop here, and we'll kind of continue looking at this example with wages, pick up where we left off at the beginning of next lecture, so that if there are any questions or issues related to this material, we can kind of dive right into that as we transition to talking about categorical variables, and then in more detail with interaction variables. Great, so thanks everyone for doing a recorded lecture. Please make sure to keep any questions that you may have. You are welcome to email me, post them to Canvas, or you can even ask Trisha. Otherwise, you can hold them for next time, and we can continue our discussion of these dummy categorical and interaction variables. Thanks all, and I will see you hopefully next week, depending on whenever you watch this video.